All right, happy Friday. If you haven't already looked at exercise 1, this is hopefully a reminder because this looks really suspiciously similar to, I'm pretty sure, Q2? Maybe? Is Q2 the exercise 1 true and falses? Whatever, there's a bunch of true and falses on your exercise, and so here are some dangerously similar, though not identical, true falses. So why don't you take the next 3 minutes, discuss true or false to each of these statements with the folks around you. The poll everywhere should be live, and I think I did it so that you need to select all that are true, if I remember correctly. But either way, I don't really care about the poll everywhere or how I double negatived myself. Go ahead, discuss for 3 minutes. All right, let's start to talk about this one. I want to spend some actual time going over this one, not only because it's on your exercises, but I know that this can get kind of annoyingly pedantic, like the language starts to become really important here. And I'm just going to say, shout out to you if English is not your first language and you have to navigate this nonsense, because even I trip myself up. So, okay. Which of these functions are true, or which of these statements are true? Before we dive into that, we have these new terms that we picked up on Wednesday. Hopefully we're familiar with the term big O, but we also learned 2 new terms, big theta and big omega. So one way to think about big O is anything that upper bounds the function you're looking at. So it's technically the set of everything that upper bounds your function. That's big O. If that's big O, can anybody tell me, do they happen to remember what big omega is? If big O is the upper, yeah, I think you were first there. Omega is the lower bound. If you remember, I showed you those annoying mathy definitions, and the only difference between omega and O is the directionality of that less than symbol. So big O is a function that upper bounds yours, and omega is one that lower bounds. So can anybody remind me what big theta is then in this case? If O is up and omega is lower, what's theta? Yeah, they're in the back. That is, I think that we're going to give you the credit for that one because it is essentially the average. That's maybe a way to think about it. To be this like annoying math person, it's like not technically average in the definition of average, but what I think you probably mean is that fit, that thing that seems to align right on top of that growth rate, and that is exactly what theta is. So if big O is the upper bound and omega is the lower bound, and maybe, the upper bound is, say, one linear and the other one's like a different linear, then the theta would be linear because the upper bound growth rate and the lower bound growth rate are in the same complexity class, and when the tightest upper bound and the tightest lower bound are in the same complexity class, then we can get what we sort of feel like is the fit, which might, in our brains sort of like feel like an average, but we're not going to use that particular word just because of the math implications of it. But that's exactly what theta is that sort of fit. We're going to get back into it. Does anyone have a question on those three definitions before we dive into even more pedantic detail on this one? Okay. Then let's start with this first statement. A big theta bound will exist for every function. True or false? How about let's do a thumbs up for true and a thumbs down for false? What are we seeing? You can look around and change your answer. I'm not judging you. Okay, yes, I agree. It is false because I gave you an example on Wednesday. This is a little bit me trying to, pull out something we talked about a couple days ago. Can anyone tell me when the theta doesn't exist? Does anyone remember what happened? Yeah. If the upper and lower have different complexity classes. So if we draw sort of like the tightest line that just kisses the top, that tightest upper bound, and that's a different complexity class than the lower bound. Our example was that is primes, where the upper bound was that sort of linear growth rate, but the lower bound was constant. Those are two different complexity classes, and so there kind of isn't that perfect fit, and thus the theta doesn't exist. So this first statement is actually false. Does anyone have any questions about that? That's a little bit just, do you remember what we talked about in lecture on Wednesday? Okay. Now let's get into some of the more annoying wordy things here. If a runtime function is big O of n squared, so you have some function. I didn't tell you what the function is, but we know that it is technically in the set of O of n squared, so it's in some way upper bounded by n squared. It cannot also be in the omega of n squared, meaning it can't also be lower bounded by n squared. Thumbs up, true. Thumbs down, false. Feel free, look around. How are we feeling? Yes, I agree with the thumbs downs in this case because this could be a function whose dominating term is the n squared term. So their tight upper bound is n squared, their tight lower bound is n squared. Thus, they have a theta of n squared. So it can technically be in all three of those categories within that same complexity class. Any questions on that one? Let's take it up a notch. Okay, a piece of code whose runtime function is f of n equals 3n plus 6. So remember, that's how we do the code model, where we start with code, and then remember we counted all of the operations, and we got this sort of like, function where n represents how many things are stored inside of whatever your structure is, or the input size. And so maybe this is an example of we have a for loop that runs n times, and maybe there's like 3 instructions inside of it, and then outside of that loop there's like 6 other fancy instructions or something that happens. Maybe that's what our code kind of looked like, but we don't care. We went from code to code model. We got, that was really direct. Thanks, Mike. I should stop moving around so much. So we've got 3n plus 6. If we have f of n equals 3n plus 6, is it in the big O of n squared, which can it be upper bounded by n squared? Thumbs up for yes, thumbs down for no. Oh, I'm trying to trick you guys with this one. You guys didn't fall for this trick? Okay, yes, the thumbs ups have it. This one is true, and you might be like, but Casey, linear is a different complexity class than n squared. Well, the complexity classes kind of have a relationship, a little bit of a hierarchical relationship against them, and anything that's in the n squared class is going to upper bound anything in the linear class. It'll also upper bound anything in the logarithmic class, anything in the constant class, because those are all ones that will be upper bounded by something that's growing at such a fast rate as n squared. We're going to look at that big O cheat sheet picture again, but n squared's in like the angry red, and all of those that are in the orange or green are technically upper bounded by any of those faster growing functions. Now, during this conversation, I've been using this word tight, and I did not define that for you, which is a very annoying professor thing to do, but we lost a section or lecture, so I kind of jumped ahead. I'll show you exactly what I mean when I say simplified and tight in a different slide, but just because it's upper bounded doesn't mean it's like as close or the exact line of upper bound, meaning it doesn't quite kiss just the top of it. It could be anything above it. But big O, by definition, is anything that is equal to or greater than. So that's why big O is a collection of anything that just upper bounds it. So this is true. Any questions on that? That tends to be the one that angers students on this first exercise. Yes?
How could big O upper bound a function if it's equal to the function?
Great question. It feels like if I'm saying upper bound, equal doesn't feel like it fits into that meaning. It's just, again, rolling back to that mathematical definition where I had my function and then my big O and that alligator mouth between them. But we include the equal sign. It's a greater than or equal is just part of the definition. So we accept equal to or anything that's greater than. And part of that equal to is because that's how we can now categorize everything regardless of their coefficients within the same category. That's why I have to accept that equal sign in there. Because then something that's 10n is in the same complexity class as something that's 3n, and that is technically the big O, so we sort of give it that greater than or equal sign there. Okay, final one. If a runtime function is in theta of n, then it could be big O of log n. So if we know that our function has that fit of linear, can it in any way be upper bounded by log n? Thumbs up for yes, thumbs down for no. Wow, okay, yeah, great. Y'all didn't even have to cheat off each other that time. I agree, thumbs down. That's not the case. Logarithmic is a slower growing function, meaning a faster running piece of code, so it cannot upper bound linear. Any questions on these pieces? Oh, yes, please. So if big theta exists, the simplified tight big O and the simplified tight omega will all be the same. So you'll have all three of them in the same complexity class, but that doesn't necessarily mean that the not tight big O couldn't be something that's greater than it, or the not tight omega could be something that's even less than. We'll look at the picture, and hopefully that'll make more sense. But good job. I'm not even going to open up the poll everywhere, but make sure that you click it, and I can give you your participation point because I subjected you all to that. Okay, great. So Project Zero, your first official turn-in was technically due last night. Listen, did I maybe creep on how many submissions there were? Was there a little bit of a concerningly low number? Is it me? If you are still working on submitting P0, you have plenty of company. But just a reminder that the P0 turn-in doesn't close until Sunday. Again, something weird happened, you didn't start your setup until Tuesday, and then you realized it was going to take you all day, and you had to go to work, or you got ill or something, whatever works for you, you're always welcome to use those late days. They're there for you. You don't have to tell anybody about them. And so we will automatically assume you want to consume a late day if you turn something in late. The late penalties don't start to apply until you've consumed all 5 of your late days. If you have something extraordinary happening in your life, contact us and we could talk about other accommodations. But please know that as of right now, the last possible time to turn in P0 will be Sunday night at 11:59 p.m. This also means that P0 is now officially out. So the instructions are on the course webpage along with a skeleton of the code. I know the code isn't sitting in your Git repos right now. We'll resolve that probably immediately after class. But I'm going to talk a little bit about P1 in a few slides here. But FYI, P1 will be due next Thursday. And P1 is your first partner assignment. Yay! And then, of course, reminder that exercise 1, it went out on Tuesday. It is going to be due next Tuesday. We will not have another lecture before that. So I sort of think of myself as having gone over everything in exercise 1 at this point. So remember, you have now until Tuesday to submit that. And remember that exercise 1 is an individual assignment. Does anyone have any administrative questions? Yes, please. There are only sets of 2, no sets of 3. Is that your question? Yes. Yes. Any other questions? Okay, cool. All right, let's talk about P1 for a hot second. So the P1 assignment is called DEX. It's like a queue, but you can add both to the front and the end. So you kind of have that like line at the bank situation, but you can also allow somebody to like cut in front. It's kind of what's happening there. So we're going to give you this ADT DEX, maybe a little bit different than something you've encountered before, and we're going to ask you to implement it using both an array and a linked list. So if you remember, we kind of talked about that in lectures 2 and lectures 3. If you want to go back and review that stuff. But again, getting you used to sort of that idea of multiple ways of implementing the same functionality. That's all. It's interesting. One thing I did want to call out, okay, so this is something you probably haven't necessarily encountered when you have been working with linked lists, at least if you came through our introductory series. And it is something we kind of set up for you in the starter code here. One, you should know a part of this class is giving you starter code that you have to go in and understand and then contribute to, because quote, in the real world, which is nonsense. We're all always in the real world. I don't know what that means. I think people just mean after school. But after school, if you're in industry, you will never start a piece of code with a blank file unless you go literally start your own company. So from here on out, you always have a bunch of code that you need to digest, understand what's going on in there. And in the code that we give you to set up DEX, we are going to give you, I think we give you the array code, and then we ask you to implement linked lists. We have you debug one, implement the other, but you still have to integrate with it. The way that we're going to ask you to implement the linked deck is using something we call sentinel nodes. So if you remember from your P0, when you're implementing linked lists, there's a lot of different cases. You end up having a lot of different if statements, like if the thing I'm interacting with is at the very front of the list, or if the thing I'm interacting with is at the very back of the list, and if it's neither of those things, then it's somewhere in the middle. It's almost like there's 3 different sets of very similar code you need to write to interact with all of those different places in the linked list. Well, what if instead you had these kind of dummy nodes that will always exist? You kind of throw one at the beginning, and you throw one at the back, and that way, everything that ever exists sort of in play of your linked list will always behave like a middle node. So you don't have to write those cases anymore, because you kind of just stick some front and end nodes in there, and then the nodes that you know you're going to interact with will never be the extreme front and the extreme end. So this is actually a pretty common technique, just a way to sort of simplify code. So here we've got a list that has the values 3 and 9 in it, but if we see down here, we actually have 4 nodes. These are the sentinel nodes. They're kind of these dummies. That feels judgmental. Sorry, sentinel nodes. But there's one here at the front, and one here at the back. They don't contain any information other than, whoa, you've hit the front, or whoa, you've hit the back. And then you see the values 3 and 9 in the middle. It'll make more sense when you get into it, but I found that if I didn't stop and explain it, people would start coding the linked list like they're used to it and not notice that this is kind of a bit of a change. Questions so far? Great. Other changes that are coming with P1. So in P0, we gave you code with some unit tests, and hopefully you got it working so like you could run it in IntelliJ and you get those like really satisfying green check marks. And then you went and you submitted it when you had all the green check marks to Gradescope and you got full credit because I was so delightful and predictive, hopefully. Well, now we are still going to give you test code, but the code we give you locally is not going to cover all of the tests that will be on the Gradescope. So just because you pass all of the green check marks locally doesn't necessarily mean you're going to get 100% when you go submit it to Gradescope. You'll still see your score, but what you might see on Gradescope then is like test failed, and then hopefully a somewhat helpful test name to give you a hint as to what went wrong. And then it's your job to go back in and write your own tests and figure things out. So, maybe you write your code. In that moment, think about the edge cases, look at the code we've given you, ask yourself what could possibly be missing here. You run your own test, you run it on Gradescope, you see you're still failing something, you read that helpful title, and you're like, oh no, I'm missing something. You go back, you write more tests, and this is us encouraging you to get in the habit now to think about what are all the different edge cases of your code, getting comfortable writing your own test cases, all of that good stuff. Yeah. I feel like that's mostly self-explanatory. Great. And then, like I said, the other sort of big change is this one is now officially your first partner project. And in fact, partners in coding are very popular and extremely common. And in fact, once upon a time, there was this idea called extreme programming. I know, okay? It was the 90s. And they were like, oh, just sitting in a dank basement by yourself, that's not extreme. Extreme programming is when you do all these really modern things to like spit out code as efficiently as possible. Because if engineers are obsessed with anything, it's efficiency. And so somebody went out and they did a bunch of research on what is the most efficient way to write code. And one of the things they came up with is this idea called pair programming. And they found research-wise, one, it cuts down on a lot of time because when you write code professionally, before we actually like accept it into the overall project, it always has to be what we refer to as code reviewed, meaning someone else on your team looks at your code and gives it a thumbs up. In fact, in most professional settings, you usually need at least 3 separate humans to give it a thumbs up. Well, if you're pair programming, meaning you write everything with a partner all the time, well, you're just automatically code reviewed. So you don't have to, say, send the code review out and then wait for your friend who doesn't wake up until noon because that's how they live their life, get it, and then for them to actually code review your thing and then send it back, and then you respond to the comments and then you send it back. It actually, there's a whole bunch of research. I will admit this happens also a lot of times across time zones and crazy things like that. Pair programming is a way to cut down on that. It also turns out you just design better code, you resolve problems faster, your communication increases. There's actually companies out there that only pair program. It's wild. So you get to practice. You're welcome. You're like, Casey, are you literally just talking about working with a buddy? Because that doesn't sound so fancy. You're right. Do what works for you. But there are sort of official ways that they've found that work really well to pair program. There's actually roles called navigator and driver. And you want to swap back and forth. If you get into a situation with your partner where one person is always coding and also always coming up with the answers, then you have another person who is essentially just hanging out. Not great for either of you. And if you're the person that's like, yeah, but Casey, I'm the typer, and like, whatever, that person can do whatever they want, guess what? The act of having to communicate your ideas to another human makes them better, makes you a better communicator, makes you better to work with. And frankly, the person that only wants to like sit here and do code by themselves, I almost can never get them through interviews. So now's the time to break yourself of that habit. I know. Lean into the discomfort. We're here. It's a community. It'll be fine, okay? There is a video here, how to pair program, that I called helpful. where somebody from Flatiron School actually walks you through how to do this transition between navigator and driver and a bunch of tips and tricks and all that sort of fun stuff. There's also this How to Pair Program YouTube video that I will let you and your partner watch for hopefully a laugh. But I really do encourage you. I say it every quarter, and I know you don't listen to me because frankly, I probably wouldn't have listened to me. Don't just split up the work and then reconvene the day before the assignment is due. You know how many uncomfortable conversations I have? Listen, I'm not judging. You're the one that's uncomfortable. When it's the day before the assignment is due, and I'm like, oh, what does this line of code mean? And you're like, I don't know, my partner wrote that. We just sort of like split it up. And I'm like, guess what? We didn't write these assignments to divide and conquer. We wrote these assignments to pair. So I encourage you all to try. But this is the last time I'm going to soapbox about it. You're adults, figure your own relationships out. Any questions about P1? Cool. Okay. Give it a try. See how it goes. If you are still looking for a partner, I believe there is a thread on the Ed board. And if you would like some in-person mixery type of interactions, there's a class here immediately after us. But if you are looking for a partner and you would like to meet a human here, go out this door, and then you can congregate. Then you'll find each other. We'll call that our very uncelebratory mixer just outside that door, so you can find one another. Cool. Any other administrative questions, anything about P1 before we actually dive into content for the day? Okay. Also, you're going to get to learn how to use Git. It'll actually be useful when there's multiple humans. I promise. It'll be nice. Okay. Okay. Oh, gross. No, I moved that to the back. Okay, so we kind of did this at the beginning. These are just reminders for you of the definitions of O, omega, and theta. So big O is the upper bound, big omega is the lower bound. You could think of big theta is equal to, and here's the definitions, and you can see there are the sort of like alligator mouths. Here it's in this direction for big O, here it's in this direction for omega, and then here your functions in the middle for theta. Delightful. Okay, so here, for example, 4n squared is lower bounded by omega of constant. That makes sense, right? 4n squared, that's going to be the n squared class. It'll be lower bounded by constant. It'll also be lower bounded by linear. It'll also technically be lower bounded by its own complexity class. But then once we get to n cubed starts to dominate that. So it is no longer in the set of omega. N to the quad, I don't even know what you call that, n to the 4, that is not a lower bound anymore. And if we look at it, oh great, thanks, this is a animation translation thing. If we look at it from the other direction, 4n squared, it is not upper bounded by constant, nor is it upper bounded by linear, but it is upper bounded by its own complexity class. And then you can see it is again upper bounded by n cubed and then upper bounded by n to the 4. And then that's where the theta is. Here we go. This is the picture I was waiting for. So this is actually a pretty helpful website, Big O cheat sheet. They actually even have like a poster you can print out if you're into that stuff. But here's a way to sort of think about maybe kind of the stack rank of how these graphs and these complexity classes relate to each other. So down here in the green, the greenest of greens, the we wish we could have it that way always, is constant, because that is the slowest growing complexity class because it's not growing, it's flat. Then the next slowest growing complexity class is logarithmic. Then we're just sort of moving in like big O's up. Then comes linear. Then comes what we call log linear, which is n log n. We'll meet a bunch of sorting algorithms that fall into that category a little later in the course. And then we leave this mostly happy orange space and we move into the red spaces, and we can see the next thing that upper bounds log linear is n squared. Then we get to those exponentials where you get 2 to the n, that they have kind of the same shape, but 2 to the n does grow much faster than n squared. And then over here, we have O of n factorial, which is really bad and means somewhat non-predictably will complete. An example of O of factorial is like BOGO sort. If you're not familiar, BOGO sort is if I took like a deck of cards and I threw them up in the air and then I gathered them and I was like, are they sorted? Nope. And then I just threw them up in the air again and I gathered them like, are they sorted? Nope. And I just did that for forever. The other classic example is if I did not make this up, some professor somewhere did, but let's say you have an entire room of chimpanzees and you give each chimpanzee a typewriter. O of n factorial is the likelihood that at some point just those chimpanzees typing on one of those keyboards will eventually write Hamlet by Shakespeare. As you can imagine, probably going to take a long time, not very predictable. So if that's one end of the runtime spectrum and then constant is the other, here's that sort of gradient and how they relate to each other in between. Yes, please.
So when we say 4n squared is lower bounded by n squared, I know we usually would drop constants.
Yes.
But would 4n squared also be lower bounded by n squared?
Yes. So what is confusing and annoying according to the definition is you're absolutely right, because you're like, why would 5 be upper bounded by 4? But we consider anything whose only differentiator is a coefficient to be within the same complexity class, and that's part of that whole like C times f of n, n naught type of thing. It just comes from the mathematical definition. So that is also part of why we just sort of drop those things out to prevent us from getting confused in the theoretical space. Any other questions? Yes?
When you use the word like type, upper bound or type lower bound, is type the technical term or is that a definition?
I love it. Okay, great. We're not even, these are just me saying the same things over again. Here we go. Thank you, friend. What a wonderful segue. Okay, so it feels a little silly to be like, well, if I say something's O of n, well, then it technically could be O of n squared and O of n cubed and 2 to the n. That feels silly, right? So here is the thing. If you are in an interview setting or you're out at work, when they ask you for the big O, because I'm just going to be real with you, they're not going to ask you for the theta, and they're not going to ask you for the omega. They don't know those terms. They forgot them in undergrad. When they ask you for the big O, what they will mean without saying it is what is the closest fit while still upper bounding things. And that's that sort of like it's kissing just the top of the graph. So we will call that the tight big O. So if I have a function that's f of n 3n, its tight big O is O of n. O of n squared is still valid, but it's not tight. It's not directly as close as we can get while still being an upper bound. So tight is what is the closest complexity class that still satisfies the big O definition. Another term you might hear us say is simplified tight. Simplified is me just being really explicit about dropping the coefficients, dropping any non-dominant terms, dropping any constant factors. So I really should have put an example on this page. But if I had f of n 4n squared plus 3n plus 10, the tight big O might be like 4n squared, but the simplified tight big O would just be n squared. So I dropped out the non-dominant terms, I dropped out the coefficient. This is all just so that I can ask you these questions on an exam, and then somebody will be like, well, I'm technically correct because I said the big O is n factorial, and that dominates everything. Ha ha, you don't think I've had that conversation? I caught you. Now I made these words, so you can't get me like that anymore, okay? I saw that student that technically printed out an 8 by 11 worksheet, but it was 8 foot by 11 foot. Fool me once, okay? Simplified tight is what I'm going to use to make it really clear on an exam what I'm asking you for. But then when you leave this class and you're in an interview, they're just going to say, what's the big O? And what they mean is simplified and tight. Questions? Oh my God, I think I've done this timing amazingly. Great. Okay. Now, we have now officially talked about 2 different phases of analysis. We've talked about code modeling, which is, remember, we start with the code, then we get that math function. We just spent a painful amount of time talking about what we'll refer to as asymptotic analysis. Asymptotic analysis is how we decide which complexity class it is. And we get asymptotic from the idea that we're looking about the trend as n tends towards infinity. Where's that asymptote as n tends towards infinity? Remember that this whole overall process is something we're going to call algorithmic analysis, and I will mix up those A's at some point, and I'm so sorry. So we just talked about asymptotic analysis. On Wednesday, we talked about code modeling. But aren't there more ways to evaluate code? Yeah, because math's fun. Let's talk more. Okay. Oh, and these are examples. You can read them. I don't think they're that interesting. Great. Cool. Let's talk about something I like to call case analysis. So let's start with an example, okay? Let's say we have the algorithm linear search. The algorithm linear search means, say, taking an array of an unknown size and something you're looking for in that array and start at index 0 and go one by one and just look at everything until you find that thing. If you find that thing, return as soon as you find it. But if that thing's not in the collection, I got to go all the way through, exit the for loop to eventually return -1, meaning I didn't find it. So let's talk about how this code may perform, not based on how many things are in the collection, but where in the collection the thing you're looking for might be. So if we're looking at this example here, what if I gave you an array 2, 3, 9, 4, 5, and I asked you to find the value 2? Well, I would come in and I would start and I would look at index 0 and I'd be like, 2, great, found it. Return. My for loop ran one time. And it didn't matter if there was 1,000,000 things in that array or 10 things in that array. I only iterated one time. Now, what if I asked you to find 8 in that array? Well, you'd come in and you'd look at index 0 and you're like, that's not 8. And then you'd look at 3 and you're like, that's not 8, that's not 8, that's not 8, that's not 8. Oh no. I never hit this inner if statement, which means I have to complete my for loop. So I had to run through every single thing in the collection to determine the thing I'm looking for is not in the collection. So what we then have is 2 different possible complexity classes, not based on how many things are stored in the array, but where the thing I'm looking for is. And that actually has a big difference, because one of them is constant runtime and one of them is linear. This is what we call case analysis, where that situation where the thing I'm looking for is at the very beginning is called the best case. And if it's not in the list, the thing I'm looking for, I had to go through all the way thing, that's called the worst case scenario. We actually end up with 2 different complexity classes, because actually we kind of end up with 2 different code models. And we hit a little bit of this, and I did this annoying thing where I was like, don't pay attention to that. We'll talk about it on Friday when we were talking about the is primes. Somebody was like, wait, do you do the code model with both the if and the else statement? No, because neither of those things can happen simultaneously. So you could have code like this where there's a branch, i.e. an if statement, and you might have 2 different code models. One for if you hit the really nice return in the beginning, and one for if you hit it at the end. 2 different complexity classes. Any questions on sort of that structure, that idea of best case, worst case in this context? Yeah, sure. Thank you for asking that question, because that, in my opinion, is the most logical question to ask. And I will tell you that all of you will at some point assume that and can get confused. So these are 2 different cases with 2 different functions. So we actually have upper and lower bounds for each of the cases. So this best case has an upper bound of constant, a lower bound of constant, a theta of constant. The worst case has an upper bound of linear, a lower bound of linear, and a theta of linear, because they are 2 different code models. At some point, your brain will think, big O is the worst case, right? Big O is the upper bound, but you could have an upper bound of the best case, and you could have an upper bound of the worst case. It's okay. I'm happy to say that multiple times. Like I said, this is the thing that will destroy, I'm sure, all of you at some point. Any other questions? Yes, sure. So asymptotic analysis is the idea that we're going to start to place code into these large categories to compare code against its like different pieces. And that's how we get that like, okay, 4n and 5n and 10n, like those might sound like they're different, but when n tends towards infinity, asymptotically, they all just kind of converge on linear. So asymptotic analysis is a way of thinking about how your code's going to perform as n tends towards infinity, and it's a way to give us sort of an apples to apples comparison. And also, frankly, because like in industry, we always think about large scale. So we need you to start thinking about like, well, what if n explodes, you know, and keeps going? Frankly, an n of 100 is always just going to happen so instantaneously. Yeah, question? So the reason when we think about while n tends to infinity is it's sort of a way for us to get, it's like sort of a way to neutralize the variable of n. It's like when n becomes infinity, then we're kind of like, it's like all apples to apples at that point. And you'll find that a lot of engineers do it to just sort of classify code. So something that just has a for loop that runs linearly, you'll hear computer engineers refer to that. They're like, oh, that's just linear. But then they might compare something that's linear to something with a nested loop, and oh, that's quadratic. And so they sort of use asymptotic analysis to, in a large, generalized, very quick, simplified way, quickly communicate a high-level difference between two pieces of code. Because that's a big difference, linear versus n squared. You might then later have a conversation where you're like, okay, well, like, does it matter if the difference is 5n or 10n for our particular use cases? But most computers move so quickly that those differences aren't super important. So computer engineers have decided we'll just do these really high-level categories of those complexity classes we talked about, and the way to get to that high-level category is to only care when n tends to infinity. Yeah?
Could you like split our code into best case and worst case? After asymptotic analysis seems a little bit like redundant to me, as we have like a max and like an equals and a lower bound, when they all just say that the function is linear, right, or it's quadratic. It seems a little bit redundant to have all three, right?
Sure, and you'll find that a lot of engineers don't really bother too much with all three. A lot of engineers will say, give me the big O, and what they're really trying to communicate to you is give me the theta. They'll never say that, but they mean give me the theta or the simplified type big O of the worst case scenario. Because we're pessimists, and that's usually what we need to account for a number of machines to support, that type of thing. But I'm giving you all these tools so you understand how those things kind of fit. And also, if you say, you know, continue on with your computer science education, you can go on and do a bunch of these in proofs, which I took out of this course. You're welcome. But the CS majors have to deal with this a bunch. So it's also part of it. Yes?
If we were given linear search and asked to find the asymptotic analysis like of linear search, would the big O be like that side and then the omega be this side?
So
Not necessarily like that, but would that, in this specific case, I'm just trying to figure out. Like,
thank you again for asking this question. We have again fallen into it is so easy for us to think of big O as worst case and omega as best case. What you would probably want to say if somebody was like, analyze linear search for me, you would probably say, well, the simplified type big O of the worst case scenario is linear. But we technically have a simplified type big O of the best case, which is constant. And so actually, now we kind of have this range. What's the best way that it could go? What's the worst way that it could go? And that means there's all sort of like variations between there that could be, you know, that's just giving us the range of performance. So that's also something you'll often hear people talk about where they're like, okay, well, what is the worst case scenario of the best case? Or even if we want to think about it faster, what is the lower bound of the best case to the upper bound of the worst case? That's the true fullest range of expression that your code could possibly execute in. And sometimes people want to analyze the range so they can think about how they partition machines and things like that. Okay, yes, please.
Is it possible for the algorithm to have a different complexity class based on the underlying architecture, or is the complexity class agnostic to the architecture?
When you say the architecture, you mean like the computer architecture on which it's running? Great question. So this is all agnostic to computer architecture because we're living totally in theory land. And the reason we're doing that is because we don't know what computer it's going to run on. And so your big O worst case on your MacBook Air is going to be really slow compared to our worst case big O on like one of the supercomputers. And so since we, as the designers of code, often don't have control over the actual machine it's going to run on, we talk about this in the theory place because we're software engineers and we let the hardware engineers deal with that. But if you are, an actual engineer, maybe you have control, and that's something to think about later on. And you can think about, well, I know the theoretical upper limits. Now I can compare that with my computer architecture and see what's going to happen. But in this context, we're lifting ourselves out of any of the physicality, any of the reality of how it's actually going to run. We're just talking theoretical. This is like a frictionless physics kind of surface type of analysis. Yeah, here in the middle. So, and I think our friend was kind of bringing this, like, it feels redundant to have all three for multiple cases. Yes, I kind of agree with that because it's pretty rare to have something different, but we could. Let's go back to that is prime example. Remember how is prime, it was helpful to have the big O versus the omega because those two were different? Well, what if you had a piece of code that already had stored, say, the first 1,000 primes in some type of quick lookup machine, and then after 1,000 you had to compute them? So you had like two different algorithms kind of mashed together into one piece of code. And so then you have a best case scenario where you've already computed the prime and a worst case scenario where you haven't computed the prime. And the worst case scenario has a big O of linear and an omega of constant. And the best case scenario, let's put it in a hash table. So it's got a big O of constant. I know I'm saying a bunch of things we haven't gotten to, but there could be, as we get into more and more complicated code, differentiators like that. Let me show you one more slide that I think will help. This is, like I said, this is the most common misunderstanding. We will spend the rest of this class making sure that this like sits clearly in your brain. But the thing that seems to confuse students most when I'm asking them like, oh, what, because I'm going to ask you on a lot of exams, what's the worst case scenario? The most common thing I will hear is, well, the worst case scenario is when n's really big. Or the best case scenario is when n is 0. That's not asymptotic analysis, because we can't pick the size. N has to always tend towards infinity. So here are some other examples of case analysis. Insertion sort, we're going to talk about that. That's a sorting algorithm that as it moves through things, when it finds something out of order, it moves it. So if you give it an already sorted list, it just kind of runs through and confirms it's sorted. So its best case is an already sorted list. So its worst case, having to do the most movements, is a reverse sorted list. Doesn't matter how many things are in the list. It's about the structure of the data within it. Or like if we have a method to remove duplicates, the best case scenario is there's no duplicates, and I just run through the whole thing, and I'm like, never mind, don't move anything. But the worst case scenario is maybe the entire thing is duplicates. Again, it's not about how many things are stored in it, but the state of the data. Yes, question in the back. So, and that is the joy of when you get into those boardrooms and you argue with engineers, because somebody will be like, well, technically the worst case is a degenerate hash table, and then some other engineer will be like, that's such an edge case, that's incredibly unlikely to happen. I'm just giving you language, and so it actually is sort of on a situation by situation basis as to the worst case, how likely that may or may not be. You'll find some code actually, there's no difference between the best and worst case. It runs exactly the same every time, like if there's no if statements. And sometimes you have a worst case that's just almost impossible to happen, but could theoretically happen. And so whether it's an edge case or not does depend on the situation. It's okay if this is confusing. I promise we will spend a bunch of this quarter jamming this into your brains. We'll see a lot more examples of it. But have an absolutely wonderful long weekend. And please turn in your assignments. If you're having difficulties, make an ed post, send us an email. Thanks so much, everyone.